Good morning. This is Professor Evans, and we're going to be talking about Chapter 2, and going to be going through it and discussing some of the basics of how a ladder diagram is put together, and I want to talk through that, and at the end of the chapter today, I want to talk about the lab that you're going to be working on, and that's found at the end of this chapter, and also some problems that I would like you to work. So in order to understand the layout of how a programmable controller describes logic, you need to understand a little bit about the background of how the logic was described prior to the implementation of a programmable controller. So that's what we're trying to do today, and it has to do with the symbology and the layout of a ladder diagram. And the symbology of the devices that were used, I have some of those here, and there are a number in addition to these, but these give you at least a starting point from which you can say, I've seen that symbol before and I understand a little bit about what it's about. Now these symbols are from Visio, and Visio is a part of Microsoft. So these are the Microsoft symbols, but you can also find the AutoCAD symbols. They're a little different. You can find other symbols that are a little different as well, but basically they're all kind of the same in that they try to replicate a physical device, and they show some methodology as to why that device works in the particular way that it works. For instance, this is a flow switch, and it has a little sail on the bottom of it for indicating of if there's some flow, it senses it going by. This is kind of a pressure idea with a little oil can there, pressure. So other ones, this is the temperature switch with a little squiggly, and the light shows the light coming out there. Now this is the symbol for a relay coil, and this would be the symbol for a normally open contact off of that coil and for normally closed contact off that coil. We're going to talk about those a lot more in this course and in this section as well. We're going to talk about that in this lab that's at the end of this chapter. So this would be symbols for European symbols, and what's the main difference was these are vertical typically, and the American symbols are laid out horizontally. But they're basically the same. So you can look at a drawing either from European drawing or American drawing, and you'll see basically the same type of flow. It's just one is structured a little differently than the other, but they're basically the same. There's a basic structure to a schematic, or we call it a schematic or a ladder diagram, and some people call it an elementary diagram, but there's a structure to it, and the basic structure is power starts at the left, ends up at the right over here at a coil or some output device. So these would be considered logic devices, things that make logic happen, and this would be the output device that would actually turn on some device or whatever. Now this does not have to be a relay. This could be a solenoid, this could be a motor starter, this could be some other device over here, but the logic that sets up that starting is always to the left, and the physical output device is always to the right. And there's a rationale for that, because, and that's how you find it in a PLC typically, flows from left to right. Because if this device were over here on the left, and let's say, for instance, something that has happened and does happen is that the wire on the left side fell off and touched a ground or a neutral, that this device would turn on without all this logic having been executed, and that's not good. Especially if you're sitting there with a motor starter and you're pushing a button and the motor won't turn off, it's running no matter what you do, you're really in a danger situation. So you want the logic constructed this way. Everything to the left gives the signal to turn on the thing at the right, and you want flow from left to right. So that's a general philosophy as to why a single rung of a ladder diagram is constructed with flow from left to right. Now, does it have to go from left to right? No. With a circuit like this, the current flows with the wire, so you can have it left to right, right to left, whatever. But in general, you want the circuit to flow left to right, and that's one of the compromises that has been done in a program controller, is that you cannot let electricity flow in a program controller right to left. It's got to flow right left to right, and that's something that you know is not real. That is just something that it is that way, and they've compromised. So it's not an exact replica of this when you put it in a PLC, but it is sort of a replica of this, in that they decided a long time ago that they were not going to have power flowing right to left in a program controller, even though it could in the real world. So if you find a drawing that does that, you may have to do some changing to it in order to redraw it so the program controller would actually allow it to have that happen. So this is a real simple circuit. This is a circuit that you may or may not ever have designed, but it's a push button, a PB, and it turns on a relay coil. Now this is the coil of a relay, and you can see the CR that stands for control relay, and it'd be the first one. CR1 is the first one. So when I push this button, I energize this coil. Now what that does is those contacts that are associated with that coil turn on. The normally open ones close, and the normally closed ones open, so you can have logic off of CR1 that you can create in other parts of your system. So basically this is a setting up of a circuit that then you can use for other things. Why couldn't you just use the contacts off the PB? Well, you could, except for the fact that this gives you a lot more contacts. Typically you would get 4 or 8 contacts off of this CR, either normally open or normally closed. So here's another circuit. This would be a circuit that would utilize controls that would start and stop the CR based on certain activity. And you notice we put the stop button first. Now the stop button is important in that it controls everything. You have it usually in series. You could have more than one start button. You could push your finger on this button, it would start the CR, or you could push your finger on this button and it would start the CR. Or you could push both of them and it would start CR, except if you have your finger on the stop button, in which case no matter what happens, this turns off. Very important that the stop button is in series as opposed to in parallel like these two start buttons are. Here is a circuit that you're going to see here, and you're going to see it later on in this chapter. You're going to see this as a push button, and that push button turns on a light. It turns on when you push this button. This light turns on. That contact closes. This is not a capacitor. This is a contact off of this relay. It's referenced off of CR1, and there it is. That's a contact off of that relay. This one was lit until you pushed PB, and when you push PB, CR1 turns on, and this one turns off. So if you were trying to have a function, let's call this function CR1. This would be CR1, and this would be the not of CR1 in Boolean. So this describes the coil, the symbol for the coil, the symbol for the normally open, and a symbol for the normally closed contact. There is a physical drawing here that shows what's actually happening. You have a coil of wire and you have terminals, and when you energize that coil, what you actually do is you magnetize a core that pushes down against a spring, and it pushes these contacts with it. So basically it pulls those contacts with it. So either it is in the up position or it's in the down position. It's either with the spring or it's fighting against the spring. So this would be a normally open contact that would, with the spring action would close, and that would be that one right there. Here's a picture of a relay, and here's the contacts. The contacts go across like this. This would be a, I think these are normally open and these are normally closed or something like that. I'm not sure, but I think this is normally open. This would be the other side of the normally open. This would be normally closed, the other side of the normally closed, etc. But this would be the coil terminal. That would be one of them, and one would be over here. And there they would be open if you open this thing up. And you would see this is that O, this is that circle for that coil. And if you energize from here to here, you're going to magnetize this base, and this is going to pull this top part down and fighting against that spring. And your contacts are going to change state. Normally opens are going to close, and normally closes are going to open when you energize from here to here. There's that O, or that circle, that you physically can see. It looks like an O, and there's the 2 points for the contact, for the coil. This is another picture of a similar device. It works exactly the same, except for these contacts have special protection, and these are for arc chutes, so that if there's a current that is, when you open the circuit, that it draws an arc, which can happen in a DC motor especially. These arc chutes protect that from getting out of hand. So basically they protect this arc that's drawn on this contact from moving over and doing something harmful someplace else. And that's a typical application of a relay. It's a special application of a relay, but these are arc chutes that keep that arc from running around and doing harm someplace else in the circuit. You would never use a standard relay for this application, whereas they do exactly the same work. You energize a coil, it pulls this down against a spring, and you would see that these contacts, when they open, they could have an arc, and at that point in time you want to protect them. Now there are other devices that we saw up in the besides relays, and one of them is a selector switch. And this is a picture of a selector switch. It's a 2-position selector switch. You can either go in this position or you can flip it over in the other position. Now this would be the symbology for us for a selector switch. If the switch is in the left position, it would go with the X. It would be on the left. If it's in the right position, it would be this one right here. So again, this is a way of expressing in a schematic diagram how this switch actually operates. Left position, right position. So it powers, in the left position it powers this circuit, in the right position it powers this circuit. And you say, where does the symbology come from? Well, typically the automotive industry and the suppliers to the automotive industry adopted a standard symbology, and that's pretty well stuck with us throughout the years. So the symbology for an X and an O is not something that you might find in some drawings, but it is found on a lot of drawings where the symbology for a selector switch is this. You say, do I have to use selector switches? Well, they're nice. You might actually have to use them in some situations. In other situations, you might be able to get away with something on an HMI. But here is something that you might consider. If you have to put a switch on a particular piece of equipment, you might have to consider all these different options for that switch. Is it a momentary or a maintained? Is it flushed or extended head? Is it a normal or a mushroom head? Do you want to put it on a wobble stick? Is it illuminated or not illuminated? These are all decisions you have to make in order to buy that switch or push button. And you're going to have to decipher whether or not that's something that you're going to end up with and you want to do or not. You might put this into a HMI panel, which would then give you the option of doing that on a screen, but you might end up having to do all these things yourself. And if you do, then you have to consider all these facts, how they're done. Okay. Now this is a push button, and this is a thing you would never want to do. I had this physically here, and I somehow finally got taken out or whatever, but you would never put that many contacts on the back of a button. Why not? Well, each of these contacts has a spring in them. So you add all of the force from all those springs, and it makes it almost impossible for the student, this guy, he was trying to push that and he couldn't. This button here is extremely hard to push, so you'd have to say, well, who would ever design something like that? Well, if you needed that many signals off of that button, you'd have to do something. If you use a programmable controller, you just run the first signal from the first contact into the programmable controller, and you can use it as many times as you want to, for many pieces of logic as you want to. However, If you were designing with a schematic and didn't have a program controller and you needed this many functions, you would have to put that many in there. You say, I would never do that. And that's true, you would never do that because you would have to run these to relays, and then the relays would actually perform the logic. You would either get 4 or 8 contacts out of every one of these signals. And that's something that you would have to consider. You'd have to count how many contacts, how many signals you had, and then buy that many appropriate relays. This is a timer. A timer is a timing head that is put on a relay. Here's the body of the relay, and here's a timing head. Now this is a pneumatic or air timer, and it actually has a little dashpot in there that time delays. If you energize this relay, you would hear a psh, and then a click, a secondary click. You'd hear the click, psh, a secondary click, and that would be the time delay click that you would have to set up with this pneumatic timer. This is something that's not very accurate, but it was useful. But again, this is something that's been replaced by the timer inside the programmable controller, which is what we're going to study. But this would be the physical device that you're replacing, the timer. These are relays. This is a relay coil, and you would never do this in a program on a schematic drawing. Why wouldn't you do this? Well, each relay is rated at a certain voltage. It has a certain resistance. And if you say, well, I'm going to use 110 volts, each of these in series would take 55 volts. So 110 would be split equally between 55 and 55. If you ran this at 55 volts, it would not energize. It would sit there and hum, and eventually would burn up, just get hot and burn up. So this is something you would never build in a schematic drawing. However, on a program controller, they let you do this. They let you put 2 of these together, and you can actually have this together if you wanted. Now, on the other hand, you could have done this, like right here. You could do this, and this would be, each of them would be in parallel. So the coils here would be allowed. Now, why would you ever do this in a program controller? One coil would give you a large number, I mean a very, very, very large number of contacts. Well, there's only one reason that I can think of that you would do that, and that would be if one person was programming this and he wanted it to say ABC. In other words, he had a label that would say a certain thing that he wanted it to be. But another person came along and wanted it to say something else. He would create a separate coil and give it a different name. So you have the same variable. This would be the same function here, but this one would have one function name, this would have another functional name, and both people would be happy. And that's actually happened in the past, where I'd be programming along and I have it named a certain way, and the guy that was doing the HMI panels thought he'd better put a different name. I come back the next day and there'd be another coil sitting there, and he had it named his way. So again, you can settle a lot of arguments if you say, well, you just put another coil there and let it go. But that's the only reason I can think of that you in a program controller would have 2 coils that were sitting there doing the same exact function. This would be a different function in that here there's this contact could be off of any signal that would turn on this coil, and this would be another signal that would turn on this coil. These are different. These have different functions, and they would work differently. This could be turning on with whatever is going on out here and this. These would be turning on with whatever happened out here and the not of this. So this is something that's totally different from this or this. And this would be for a light. A light could be an output. You could have the light could be turning on off of something like this, or something else could be turning on from this function as well. So again, that'd be totally different, but the light is at the end. So how do you put relays together? Well, you can put them together in Boolean logic, and here's some of the examples of Boolean logic. Here would be the and this would be the way it'd be written in Boolean, the Boolean equation. This would be how it would be shown in ladder logic. A and B give me an output coil of X. So my output is my coil, my contacts, and these could be from any relay. Any relay, I would get an output X. So a contact off a relay A and a contact off a relay B, normally open, give me output X. This would be an OR. A or B give me an output. This is a NAND, which is a not or. A knotted or B knotted give me output X. That is the NAND. This is the NOR. This is the exclusive OR. You could also have the exclusive NOR. I didn't put that in, but you could have it. And this is the NOT. So what are the names that people use for various contacts? The Americans usually say normally open, normally closed, and that's what I typically would say. The Europeans would say the make and the break. This would be the make contact. This would be the break contact. So they use the term make and break as opposed to normally open, normally closed. This would be a symbol for a circuit with a AND of a normally open or a make and another make and an output or an indicator light in this case. Okay, so I want to talk a little bit about motor control. Even though we're not going to be starting any motors in this class, I want you to understand that there's a parallel set of circumstances where you're either talking about logic to turn on various devices or you're talking about logic to turn on a motor, and it's very similar in the fact that both of them have like a coil for a relay. And here is where you would start. You would start with taking the power from two of the phases or two of the legs of the motor starter, and you would take them through fuses. You take them through a transformer, step-down transformer to typically 110 volts. So an L1 would be a lighting circuit, or an X1 would be a control circuit, and you would have the neutral over here on the right, and you would ground the neutral. You would tie it to some kind of a grounding terminal. Now this is as simple as we could have a switch closing and turning on a light. You could do the same for 24 volts. You could also have parallel circuits if you wanted to. And you would need to put the wiring together so you would actually show that all these are the same wire in a situation like this. You have to have wiring numbers. You have to have wiring numbers in these circuits. So here is a circuit for a motor. The simplest motor circuit you could have for a three-phase induction, squirrel cage induction motor that would start in a factory. So I have a contactor for each of the three phases that work off of the same plunger. So you have three contactors, not three contacts, not just one. And these are motor rated contacts for that particular motor. They're fairly heavy duty contacts. They're not relay contacts. They're motor contacts, but they act the same. You pull in a coil, these three energize and turn on. These are sensors. They're devices that are set for a certain current, and if they go above that current, they heat up a device that will set up a switch that'll turn the motor off. So in other words, these are not the switch, but they interact with a switch that'll allow the switch to turn off the motor. So this is a sensor. You have a sensor in each of the legs, and those are called your overload. They're called your overloads. Then there's an overload switch, which we'll talk about in a little bit. Then you come out to these terminals called T-leads, and then you go to your motor. This could be 5 feet away, it could be 100 feet away. But basically, this is your motor starter. This is where the ending of your motor starter is, and then you go out to your motor. So that's a three-phase motor starter. That's what's going on inside. Now, what feeds that motor starter is something ahead of it that protects you from inrush currents, high inrush currents. One would be a fuse disconnect. Fuses can be used to protect your motor starter. Another would be a thermal breaker. Another would be a magnetic circuit breaker or a thermomagnetic circuit breaker. Any of these devices could be used to stop the inrush of current if you had a dead short in your motor starter or outside toward your motor. Now this is a picture of a forward reversing motor starter with the forward and reversing contacts. What we have here is the same as what we had before, except we now have a set of contacts, three contacts that flip two of the phases. So here's our forward contacts, here's our reversing contacts. So what do we have with the reversing contacts? Well, with the reversing contacts, by the way, these and these cannot be on at the same time. You either are doing this or you're doing this. You cannot have both on at the same time. So what do we have? If the reverse, the phase 3 wire is the same wire. The phase 2 and the phase 1 are flipped. Can you see that? Phase 2 and phase 1 are flipped. Now, any two wires can be used. In other words, I don't have to flip phase 1 and phase 2. I could flip phase 1 and phase 3, or phase 2 and phase 3. It doesn't matter. But I have to flip any two of the three phases in order to reverse the direction of my squirrel cage induction motor. That's how that's done. So here's a simple forward-reverse circuit that would either turn on in forward or turn on in reverse. And there's my overload. The overload circuit, if you get too hot in any one of the three phases, too high current, it'll turn off in your circuit. This is a circuit that you could use to start the motor in forward with a forward push button, or in reverse with a reverse push button with a common stop push button. Again, the stop button is out here in front. It's the very first thing. Then you have your forward button, and it would turn this on. Obviously, if the reverse is on, it would block it. If the forward can be turned on, however you push this button and it turns this on, you have a feedback here. This is a seal that actually feeds back and shows you this seal right here, and it sets this up so that you can lift your finger off this button and the forward will stay running. To stop the motor, you push the stop button. Now if I want to go in reverse, I push the reverse button. Forward can't be running, and the coil turns on, and it gives me this feedback, and it seals it in, and it stays running even though I walk away and take my finger off the button. So in this circuit, I can start the motor in the forward direction or in the reverse direction. Now you say, what happens if these contacts fail? There's also a mechanical lever inside a forward reversing motor starter that will not allow the coils to both energize at the same time. So these are protected from turning on both mechanically and electrically. Both have to, you cannot start both of these at the same time. If you do, you're shorting your motor, and that's not good. Some of these are pictures of push buttons and selector switches, and I'm just going to leave these for you to look at as circuits that you can observe. Various push buttons and selector switch combinations allow you to make choices as to what you're going to do in a certain application. So again, we're not going to go in depth. This is a picture, however, of a motor starter that gives you the picture of the physical device. Here you're bringing your three leads in from the power, and here you go out to your motor. These are your T leads right here. This is the body of your motor starter. This is where your motor coil is, and where you energize so that you can actually start the motor. These are these auxiliary contacts on the side that allow you to have the feedback for your motor starter. In other words, this would be where you would actually have these contacts that would give you the path that goes around your push button. These are called auxiliary contacts. The overload has three sensors, one for each phase, and there's a contact that comes out here that's a normally closed contact that if the wire in any one of these phases gets too hot, too much current, this will open and turn off your motor starter. So that you put that in your circuit, and that will protect you using the overloads. Right here's a picture of that motor starter. And then the layout of the parts. Here you can see the contact for the overload right there. There's one of the contacts, the other one's right behind it. Here's the contacts. You can see one right there and one right there. These are the contacts for the overload. Here is the physical overloads, the devices. Here's your coil, the two terminals for your coil for your starter, and here's your auxiliary contacts right there. All the parts are laid out on this one. This is physically being able to push that contactor up, and you can actually hear it click when it turns on. These are heavy contact blocks, and they have a lot of capability of a lot of current going through them, so you can actually physically push that in and it'll turn on. Just an aside about the National Electric Code, we are dedicating a little bit of time every once in a while to talking about the National Electric Code. You should, once you get a job, have a copy of the National Electric Code available, either in a library or on your desk. And my recommendation is on your desk, so that when you have problems or when you have questions, that you can actually have a copy of it, so that you don't have to go borrow it from somebody else. And it's a very good book to at least know where things are located. Every one that I've ever had when I've been working in industry, I've had tabs for dog-eared for pages that give me the ideas where to turn for specific application. Now this is a simple application, but it tells you basically the ohms per foot of various sizes of AWG wire, American wire gauge wire. So a 14, a 12, a 10, and an 8, and these are useful wire gauges. And again, you may not have to make this calculation a lot, but you do need to know these things. So basically, if you were to say, why do I need this? If you run a solenoid too far, if you run it more, the application that Owens Corning was always 200 feet, more than 200 feet, you needed to run a AWG wire gauge. From 14, you would go to a 12, because the inrush current was higher than the running current or the settled current of a solenoid. So the inrush current would have to be high enough that the voltage drop at the solenoid was enough it wouldn't pull in. So you'd say, you had to remember that? Well, usually we just said 200 feet or longer, you'd have to put a solenoid at a 12 gauge instead of 14 gauge. We knew some rules of thumb, but where did those rules have come from? They came from the National Electric Code. So we had to know enough about where this was in the National Electric Code that if we had to go back and calculate it, we could, and this is where our calculations all came from. So again, you may or may not have ever seen a copy of the National Electric Code, but when you work in industry, you will have to use it from time to time. And this is just a simple application, application that you could use, and there are many, 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 many more. Now we're going to get into the lab, and the lab that you're going to be doing, you're just going to do a report. I'm going to download the lab for you, and you just report on what you see for the lab at the end of chapter 2. That's all you're going to do. There's nothing else that you have to do. So the report at the end of chapter 2 is a report on, there's two things you're going to hand in. The report at the end of chapter 2 on chapter 2, and then a report on this lab. And at the end of chapter 2, this lab it starts right here. It's on page 26 through, I think, 34, and we're just going to, you look at the video, and then you write us a report answering the questions is all you have to do. So here is this relay. Now this is a potted relay that I took the side off of so that you could see what was inside of it. This is a 12-volt relay. This would be used in a car, automotive application. 12 volts is typically used in cars. But down here is another relay that we now have a bunch of, and this one is a 24-volt relay. These are Omron relays, and they're very similar to the ones up above. They're DC relays, but these can be used with 24 volts, and this is the one that I'm actually going to show you in the video how it works. So basically, you can answer the questions based on this one. And here is the schematic for the various parts of that relay. Here's the coil. If you wire 24 volts plus here and minus here, this coil turns on, and I do that in the video. When that happens, the contact between 9 and 1 it was closed, it'll open. The contact from 9 to 5 was open, now it closes, so you will actually see that, and you'll see the results of that. This is the layout of the socket. So the pins, 14 and 13 are your coil, and 1, 5, and 9 are the one set of contacts, 4, 8, and 12 are the other set of contacts. So you can see those physically there, and I point that out in the lab. This is another device that we use, and you'll see it as well. This is both a push button and a light or an indicator. So there's both on each of these three. Now the row across here at the top, these are the normally closed buttons, these are normally open, and these are normally open. So you can see these actually in operation. So this is the contact from here to here for the normally closed. The red is normally closed. This is for the light. If you put 24 volts between here and here, your light turns on. Now this is an LED light, but it has an internal resistor built in so that it doesn't burn up the light if you put 24 volts across it. If you were to put 24 volts across an LED that you put out, that you just have in a kit, it'd burn up. So you have to put a resistor in series with an LED in order to get it to not burn up. So probably about a 5K resistor with a 24 volt would be sufficient to give you the light of the LED, but to not burn it up. This one, you can put it in any direction, it'll turn on. And you don't have to worry about a resistor. This is a normally open contact. So again, here's a picture of a schematic, and we would turn that switch on and we would hear this relay click. You have to answer this question: what happens when the switch closes? You physically see a contact movement and you hear a click. So we come down here and we wire this circuit, and you ask the question, what happens when you turn this circuit on? So if I push this button, it turns on this relay. If I push this button, it turns on this relay. I have this one and this one, it turns this on. So when does this turn on? We have to fill in this right down here. If they're both on, it's on, the light is on, otherwise they're off, and that's the answer for those 4 blocks. I'm going to let you fill these in, but I do want you to answer these. This would be another circuit. Okay, so this is the last circuit that I built in the lab, and here is a normally closed button, and here's a normally open button. So if I were to push this button, what would happen? The PB2. Well, this would turn on, CR1. CR1 would then energize this contact, and it would feed back this right here. Now it would stay energized even though I lift my finger off this button until I come over here and push PB1. At that point in time, it would turn off. If I hold my finger on both buttons at the same time, it would be in the off position. If I added more buttons, if I added more of these buttons, I could have it starting, this circuit starting from multiple locations. If I added more buttons over here, I could stop it from multiple locations. And what I'm actually saying is, I could take this button and locate it in one spot. I could locate this button in another spot, and I could have a start and stop for this coil in multiple locations. In other words, I could have one downstairs and I could have one up on the roof for a fan that might be on the roof. But this gives me the ability to have multiple locations. And this is all that I'm asking you to do for that lab, is make those observations and then stop. This would be the last part of that lab, and then you're done. You answer those questions and you're done. So that would be your lab at the end of chapter 2. You can skip lab 2.2, although it's interesting, just please skip it and go down and you can answer a few of the questions at the end of this chapter. You can look through these and answer these, but I don't expect you to send these in with your report. I do want you to answer number 9, number 10, and number 16. 9, 10, and 16. So with your report that you send in for chapter 2, please answer those 3 questions. And I also want to talk for a minute about this. This is at the end of chapter 2, but this is a switch that almost bankrupted a company. You say, how could a switch bankrupt a company? Well, it worked out that this was a switch that was designed for the start of a motor on a Ford various vehicles, and the design was cheap, and they eventually found it out, actually a policeman found it out, that there had been some accidents that had been started by something, they didn't know what, but this switch, if you just hit the switch, it would turn the motor off. If you just hit the keys, just ding the keys a little bit with your knee, it would turn the motor off. And that is a very dangerous thing. So it came back to the company, and the designer of this switch found that out, and he made a change to that switch. He did not record it as a change, he just ordered the change to be done. When you're making changes to drawings, you always need to list the revision level and what you did, and he didn't do that. He just pretended that it was okay with the new change, with the change that he made. It was the original, which then lawyers came back after the fact and was looking at these drawings to see if there in fact had been a change to that drawing, and they saw no change. And everybody that was around there just either if they knew about it, they would not admit it, or they didn't know. But this engineer cost a lot of money by not being willing to either make the revision on the drawing or admit that he had made a revision to that switch. He said he'd never made a revision to the switch. The people were blind, that they thought it was the same switch as it always been, and that wasn't the problem because the switch now was working. So it was a lie, and it cost the company a lot of money. I don't know exactly how it all occurred, but they said it was the switch that almost bankrupted GM. So again, why am I talking to you about this? It's an ethics issue. It's an issue of being honest in writing down what you did when you did it, and being able to fess up to things, and even though it may not have been right, needed to report it as what you did and how you did it, and then not lie about it. And that switch almost cost GM the company. So draw the ladder equivalent logic of that. So how would you do that? Well, first of all, you would say contact for A and contact for B and contact for C would go to a coil of Y. And that would be all you'd have to write for that one. 10, you would say A or B. That's an OR function, so you'd say A, and then in parallel would be B. And then you would say C with the normally closed function, and that would be ANDed together to give you output Y. Again, that's all that would take. And 16, what happens when the button is pushed? Here it is CR1 or not CR2 would give me output. So one CR2 is off, push button 2 is off. So this would be a 1, this would be a okay, CR2 would be the not of, okay, so the not of CR2, which would be push button 2, so push button 1, push button 2, so the not, okay, if push button 2 is off, this would be a 1 here, it'd be a 1 here, or CR1 is, excuse me, push button 2 is off, 1, and 1. And then push button 1 is on, there'd be a 1 here. So it'd be a 1, a 1, a 1, a 0. Those would be your answers for that one. So that would give you those answers. We're looking back at Chapter 2. Some problems here, and we just want to talk through a few of them. And just to review a little bit, number 1, if you look at that one on page 38, it's an OR. So if I were to answer that from a relay point of view, I would do an OR like this, and I would say A or B gives me output Y, and my Y is my output or my coil. Number 2, I think you get the idea here, is an AND. So an AND circuit from digital logic would be like this in a PLC. Number 3, the not of A is output Y. So the not of A is output Y. If A is on, Y is off. If A is off, Y is on. For the NAND is the not or, so basically we would say if A is off or B is off. That is the not or. So the NAND is the function is equal to the not or function. And we could write that like this. This is my output Y. And the only way that this is not going to pass power is if A and B are both on. And number 5 is a NOR function, which is the not and. And it is like this. The not of A and the not of B give me my output Y. The only time this turns on is if A and B are both off. If either one of them is on, Y is not on. The exclusive OR is number 6, and this one looks like this, and it's kind of interesting because the PLC does not have an instruction for exclusive OR, but the FBD function block diagram does. So A but not B, or not A and B. Give me my output Y. This is the exclusive OR. Okay, number 7. What a specification? So you may look that up yourself. I just want you to know that these are things that you can check up on. And you may end up writing a specification at some time in your life. If you do, be very careful and be very good at it. What kind of PLC number 8 would you expect in a Japanese plant? Mitsubishi or Omron, right? Okay, number 9. This is one I ask you to look at. This is an AND, A and B and C. This is a function with 3 inputs. Give me my output Y. Number 10, which I also ask you to look at. A or B, so you do A or B. And that is ANDed with the not of C. That gives me my output Y. Number 11, physical device that looks like a flow switch or a liquid level switch. What device in the bathroom looks like this? This is the float in the back of your toilet. That's what that looks like. Okay. And the other one was number 16. And I'm going to skip the ones with the motor starter, and we're going to go to number 16. So number 16 looks like this. Chapter 2, I've got a bus bar on the left-hand side, and I've got a push button here. I push this button, it gives me a relay, call it CR1. Control relay 1. I have another push button that goes to another relay, and that goes to another relay called CR2. And then I do CR1 or not CR2. And we're going to do a light here. So we're going to build a table called a truth table. And we're going to ask the question, when is this puppy on? Okay. And here's PB1 up here, off. And on. This is PB2, off and on. And if they're both off, do we pass power? Well, CR2 does, so this would be a 1. If PB2 is off and PB1 is on, do we pass power? Yes, we pass power both ways. If PB2 is on, that knocks this one out, and CR1 is not on, that does not pass power. If PB1 is on, we go this way, and we've got a 1 there. So there's our answer for this question. If CR1, which is PB1, is off, and CR2 is on, that's the only one that gives us a 0 answer. Okay, and the answer to number 17, what was the underlying problem with the switch from hell? This had to do with an employee who made changes to a specification or to a part, and then he buried the changes by not showing the updates to the changes on the appropriate drawings, and then he lied about it. So he did not update drawings correctly, and then lied, and that caused all kinds of problems. He covered his tracks and nobody knew about it, and for years they were fighting shadows because they thought they had a switch that worked, and in fact they had a lot of switches out there that did not work. Okay, so that gets us through the questions at the end of chapter 2. Hello. With this section, I'm going to be talking to you about relays, and we're going to look at some different relays, and I'm going to show you how they physically look. So some of these are relays that would go on a DIN rail. This would go on a DIN rail. This is a machine tool relay right here. This is the machine tool relay like what you would have found in a factory in the 1950s, 1960s, 1970s. This is a little bit smaller IEC version of that relay, and these have contacts in here that open and close when you energize the coil, and the coil is between these two from here to here, and this would be the coil taken out and looked at. It looks like an O, and that's what we're going to talk about, an O for the symbol for a coil. And this would be the top part, or the spring part, that would push the contacts up, and then when energized they would go down, and they would be in this down position. Now I'm going to energize this relay. This is a 110 volt relay, and I'm going to energize it, and I'm going to you can see what the power is when this thing turns on. So that gives you a little bit of an idea about how strong the relay is when it pulls in. And this would be, it would be sitting there. This would be the bottom half. This would be the top half. And you can see the two halves of the relay. Okay. As like I said, there's a lot of different types of relays, and I have some of them right here. This is one. This would be probably a 24 volt relay, and this one would be used for controls. This would be like a Form C relay for controls. This is another small relay that would be useful for controls, and this would be a machine tool relay that could be useful for about anything that you would have in your factory. Same way with this one. This is a little bit smaller, but it's the same style as this one. This one's a bigger one, but they do the same thing. here is a potted relay, and I want to show you, this would be like what would be found in a car, relay that would be found in a car. And maybe we can't see this, but if possible, the coil is right here, and if you touch it to you can actually, you might be able to see the contacts actually moving inside that potted relay. Okay, that's a little relay that we've used in the past, and it's a potted relay. So this is the relay that we're going to be working with in this lab, and it's found at the end of chapter 2. And this is the picture of that relay. That's on page 28. And then on page 29 of the chapter is this page right here. And in it, it shows the connection of the various terminals. So we see terminal 13 and terminal 14 at the bottom. So this is terminal 14, this is terminal 13. And we see if we wire the plus to 14 and the minus to 13, 24 volts, this relay will energize or turn on. We also see a connection between terminal 1, terminal 9, and terminal 5. If we were to take a voltmeter and measure from terminal 1 over here on the left to terminal 5 on the left, we would see it is closed. Without energy, it is closed. We see between 9 and 5 that it is open. Now, in the next minute, I'm going to wire this up, and then we're going to see that this actually changes, that we can actually see the relay moving, and the combination of 1 to 9 will open and 9 to 5 will close. Okay, now we have the plus wire, the red wire, and the 0 wire, the black wire. And as I turn on, as I touch pin 14, you can see the relay, you can physically see it change positions, and the green light comes on. So that's a symbol that it has changed, so that the normally closed contact will open. So 1 to 5 will now be open, and 5 to 9 will now be closed. Same way with the 4 to 12 will be open, and the 12 to 8 terminal will be closed. Now we're going to look at some push buttons that are also lights, and we're going to look at that with respect to what's going on page 32 of our text. So here is a set of push buttons. These are normally closed buttons, and these are normally open buttons, and these are normally open buttons. Now on the back, there's also a pin for a light. You can see that there is both. There is a red or a green. Those are the normally closed, and those are the normally open contacts. And on the other side, there is a contact for a light. So I'm going to be wiring up the circuit on page 32, and we'll test it and see if it works. So now we have wired the plus to the button. We come over here, and here's our plus wire coming to the button, and here's our button, and then we go from the button to the relay. So if I push the button, the relay energizes. You can see that. You can see the light turning on. And you can also see this over here, which is the second part of the circuit, which I now go to pin 9 of the circuit, and I utilize pin 9 over here. That's pin 9 right there. Okay, and then I go to the normally open would be pin 5, and the normally closed would be pin 1. So I wire that circuit, and I see what I got. So if I push the button, what happens? Whoops, got to push the right button, Ted. Look at the lights change the positions. So this is an example of wiring of a push button and then going through a relay, a CR, to turning on one light and turning off another light. That's the circuit at the top of page 32. Now I'm going to let you design and think through how the circuit at the bottom of page 32, fill in the table at the top of page 33, fill in the table in the middle of page 33, and then at the bottom of page 33, I'm going to let you do those on your own, figure out how that would work. I will come back and wire the circuit on page 34, and we'll see how that circuit works. So now we are at the end of our story, and we've got the hookup for the page 34 system here. And so we go through the push button, the normally closed push button first, then we go through the normally open push button, then we go from there to the coil. But then we do something kind of interesting. We go use a contact off of that coil to feed back to that contact. So basically what we've done is we've given an alternate path. So if I push my stop button, nothing happens. I push my start button, what happens? The relay turns on and the light lights. If I hit the stop button, it turns off. And that is a seal circuit. That's a memory circuit. That's the simplest memory circuit that you can have. Basically, we could add more contacts than we do at the bottom of page 34 in parallel for the start, and more in series to the left for the start, or for the stop, excuse me. Now you say, well, where does this come in handy at? Well, I can think of a million cases where you're going to have a memory circuit that you say, I want to turn on, and then something else comes along and turns it off. You don't want to have to hold your finger on that button the entire time that you're doing this. So basically, it's a very simple way of having a memory circuit. We're going to talk a lot about memory circuits in this course, but this is the first one that you will have seen. Take care.